Good morning, everyone. Hope you guys are having a good start to your Wednesday, the 2nd. We've got class today, class tomorrow, and then we've got a break on Friday. Um, and I hope with that you guys have some exciting plans for the weekend. I hope that you're gonna get some time to relax. Um, Now, with that in mind, we are going to go ahead and return to where we were yesterday with our jump off point. If you remember yesterday, at the tail end of class, what we were talking about was we were getting into some calculations. Specifically, we were looking at temperature changes. We were also talking about measurements and, you know, more or less we were looking into precision. So how precise of a measurement can you make? For example, yesterday I asked, is this number, is it 1.7230 times 10 to the second? Or is it 1.723 times 10 to the second? And there were a couple of folks who said, oh, I think it's this. And then we talked about how, well, that number right there, well, it's not highlighted on this instrument. So that's not really a part of this measurement. So you do not have that level of accuracy with this. And so, my takeaway message from that is anytime you see an instrument like this, if it tells you a number, believe it. Just go ahead and think like, okay, well, yeah, that is the mass that is being reported by this instrument, so that must be right. Um, if it read out 0.300005 grams, well, then it would be a very, very precise tool. And as a tool or as an instrument gets more and more precise, it also gets more and more expensive because of its technical accuracy. Okay, so we talked about measuring mass, talked about measuring volumes, length, time, and temperature. And temperature was a place where we got into conversions. For example, um, many times in this class, what we're going to talk about is temperature in Kelvin versus temperature in degrees Celsius. And when we compare these two, we are looking at going from one to the other. So if you see something that is 446 Kelvin, and I ask the question, what is this temperature in degrees Celsius? Well, then what you'd do is you'd say 446. Oh, how did that happen? 446 minus 273. And you get 3, 7, 1. So you get 173 Kelvin. So that is the kind of heart of this sort of calculation. To go from K to degree C, simply subtract 273 from Kelvin. Okay, and then vice versa. To go from degrees Celsius to Kelvin, simply add 273 to degrees Celsius to get Kelvin. Okay, so that's kind of the 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 calculations that we had for yesterday. Um, there aren't a lot more from yesterday's class because lots of what we talked about was we talked about measuring matter. We also talked about kind of continued and completed our discussion of physical and chemical properties. So I would say that a summary from, let's see, 0701 was our summary, was finished, chemical and physical properties. Then we talked about scientific notation. Then we talked about prefixes. And after prefixes, we talked about temp conversions. And I'm going to say measurements. Now, the last thing that I want to kind of say as like a summary before I ask a couple of questions is this Fahrenheit scale. That's the temperature scale that we're accustomed to using. And I did want you to know a couple of like major points. I don't want you to memorize or figure out how to do the conversion because that's not really a part of what we're going into, but I do want you guys to know kind of the I guess you could say standards or the ranges that the Fahrenheit scale is in. So whenever we talk about the physical property of something, we're always interested in changing state. So a solid to a liquid to a gas. And so we want to make point or make a note of some of these. The Fahrenheit boiling point of water is 212. The freezing point of water is 32 degrees. Average body temperature is 98 and average room temperature 68. These temperatures related to Celsius scale are 100, 37, 20, and 0 respectively. Now, just to bring up or to ask you guys a couple of questions, and I'd like you to respond in the chat to this. If I have one, sorry, just a second. There we go. If I have $1 kilodollar, how many dollars do I have? Add it to the chat. Add your number to the chat. Perfect. 1,000. I've got $1,000. So then if I have, if I have, and this is going in the other direction, I'm going to toggle back to this slide deck here. What's important is to remember whenever I talk about your base unit, your dollar, your gram, or whatever, that's right here where I'm putting these X's. So if I told you that I had $1 centidollar, how many dollars? And before you answer that, if somebody approached you and they had a single penny and they said, "Hey, I have a dollar," you'd say, "Well, no, you don't. You have 1 penny." If they said, "Well, I have point something of a dollar," what would they say that they have? Add it to the chat. How many dollars do you have if you have $1 centidollar? .01. Perfect. Because I have 1% of a dollar. Okay, cool. Now these prefixes, I think, are something that we have like customs that we use them in. For instance, a centimeter is something that you've seen, probably a millimeter as well. Um, and then we have them in like 1 cent, but we don't usually apply it necessarily. Okay, so remember on this slide right here, the range that you'll be asked about on exams is from here to here. Oh, and while I got you on this slide, on your exams, you are permitted to use a 3x5 index card or piece of paper, 3 inches by 5 inches. And so you can write whatever notes you want on there. You can type on there, whatever you want. It's your call. Um, and you can take that to the testing period, or you take it to the testing center if you're taking your exams there, or if you're taking it online, you're welcome to bring it there. Okay, so now I'm going to go ahead and proceed to bring us to today. Density. Now, if you remember, density, is that a physical or a chemical property? If it's a chemical property, type C. If it's a physical property, type P into the chat. Perfect. Now, the density of a substance, like if you had gold, the density of gold is never going to change. The density, so that is, it's known commonly as a, or it's referred to as a intensive property, because that's something that it's an intensive physical property. It's never going to change. Now, in order to navigate through what density is, well, we know what the mass of an object is, and we know what the volume that something occupies is. And we have an equation for this. D equals M over V. Now, our common units for density that we'll see more times than any is grams per milliliter. Now, this question right here, what are the units of density? G per ml or kg per ml? Well, think about this. How many, I'll just tell you that G per ml is equal to kg per liter. And one way to think about that is how many G in a kg? 1,000. How many ml in a liter? That too is 1,000. And what happens whenever you have, actually, answer in the chat, what's 1,000 over 1,000? Exactly, 1. So that's why you can go ahead and operate under the idea that grams per milliliter is the same as kilograms per liter. Now, we've already answered density is a physical property. Density of liquids, well, when you think about the density of liquids, it's kind of straightforward to think about the volume of a liquid, because you pour into a graduated cylinder, or you pour into a Diet Dr. Pepper can. Oh, okay, well, I can see on here the volume is 355 milliliters or 12 ounces. 355 milliliters. But what's the mass of that? Ooh, well, I typically don't measure the mass of a liquid. We do know that density of water is 1 gram per milliliter. And water is pretty commonly a standard that we use in chemistry and in science in general, because what is 3/4 of the earth covered with? Water. It's pretty abundant. It's pretty important. I'm drinking coffee, and I got some news for everyone. I used water to make this coffee. Water is the delivery agent of my caffeine and what are those organic compounds? Tannins, I think. So density of a liquid. Many liquids have different densities. Now, tell me in the chat. Well, actually, let's look at it numerically. Object A, I'll just say object 1, density equals 3.5 grams per milliliter. Object 2, density is 0.7 grams per milliliter. Okay. Now tell me, if I had 1 milliliter of object one, I have 1 milliliter of it. Tell me in the chat, what is the mass of that 1 milliliter? If I put that 1 milliliter on a digital balance, what would it tell me? The mass is going to be 3.5. Perfect. Okay. Now for object number two, let's say that I had 1 milliliter of that. What is my object's mass if I have exactly 1 milliliter of it? Perfect. Or sorry, this is 3.5 grams, 0.7 grams. Okay. So can you give me a number in the chat if you are wrapping your mind around the calculation mass over volume, or a letter if you're like, I'm a little bit mixed up on this. Okay. Okay. So if you think back to like I think I think it was in a geometry class. Yeah, in geometry um you learn about volume and calculations related to this. Um, so in order to calculate volume, you take length, and I'm going to say volume of a rectangle. You take the length of that rectangle times the width times the height. Sorry, I did a switch-o change-o. Height times length times width. Can you give me a number in the chat? If okay, I remember that. I gotcha. And a letter in the chat if you're like, wait a minute, stop the press. To visualize that, it kind of looks like this. And this is the point in the class where I don't like to be a grandstanding, like braggy sort of person, but you guys are about to see like maybe one of the top, I'd say top 15 um boxes drawn, period. So just buckle up. It's gonna get pretty impressive. Boom. I mean, this is like I'm drawing on 2 dimensions, and all of a sudden, what I have here, what, 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 what? Whoa. Oh my gosh. It's like I just drew what you see when you put one of those Oculus things on. Sorry. Okay. I'm back. I'm back. Thank you, Ashton. You're not wrong. So I know, I know. And it is. So in any one of these dimensions, you could say, okay, well, here's the width of it, here's the length of it, and here's the height. If you had those numbers, you multiply all those, and you get the volume. Is everyone good with that? Give me a number in the chat if, okay, I'm like doubling and tripling down. Yes, I'm good with this. A letter if never seen this before. Okay, cool. So what I think is really helpful to do is to think about, well, I've seen like, if I can imagine that I have a container that is 1 centimeter by 1 centimeter by 1 centimeter. Would everyone agree that that is a centimeter times a centimeter times a centimeter? Give me a number in the chat if you agree with that, or a letter if you're like, no, I don't think so. Okay. Now, when you multiply three of the same thing by themselves, what's another way of phrasing that? Or what's another way of describing that? Like a centimeter cubed. Okay. If you have something that is a centimeter cubed, what's another unit measurement? Maybe something that you see on like a Diet Dr. Pepper can for that same unit. I'll give you a hint. It starts with a M. A milliliter. Perfect. Okay. So what I try to do is, let's say that I had coffee and I was like, you know what? I need to figure out the density of coffee, which, spoiler alert, it's going to be very, very close to 1 gram per milliliter because water is 1 gram per milliliter. But if I wanted to know exactly what it is, I could get basically a cube. Now, this would be hard because it'd have to be frozen, because if I tried to make it, or I could have like a, say a container that was 1 centimeter by 1 centimeter by 1 centimeter, I could fill it with coffee. And that would give me my 1 cubic centimeter or my 1 milliliter of coffee. So let's say that I'm going to change this from object one to liquid. And let's say that I got that container and I poured this liquid one into a container that was 1 centimeter by 1 centimeter by 1 centimeter. What's the mass of that liquid? Add it to the chat. .5 grams. You're absolutely right. Okay. Can I get a number in the chat if you say, okay, cool, I got it, or a letter in the chat if you say, still mixed up on this? If you're still mixed up on this, I understand that happens. And we can revisit it. But what I think is very helpful is to just kind of imagine that, okay, you've got a liquid and you pour, like you make a mold basically, or you have a what's the word that I'm looking for? A mold or a ice tray that you pour 1 cubic centimeter. And that 1 cubic centimeter of liquid number one here has a mass. Well, the volume is 1 milliliter because it's 1 centimeter by 1 centimeter by 1 centimeter. It's 1 milliliter because 1 cubic centimeter is the same as 1 milliliter. It has a mass of 3.5 grams. Okay, so liquids have different densities. Now, what do you know about the density of water, liquid water versus solid water? Now, solid water is, well, it's just ice. Which one of these is more dense, A or B? Okay. So another way to think about this, when you when you get a glass of water and you put some solid water inside of it, also known as an ice cube, what happens to the ice cube? Add it to the chat what an ice cube does when you add it to water. I'm looking for one word. Okay. Not what I was looking for. Eventually it does. Floats. There we go. Thank you, Didier. That's what I was looking for. An ice cube's going to float. So a solid water or a solid chunk of water is going to float. Would everyone agree with that statement? Give me a number in the chat if you agree that ice floats in water. Okay. Now, I'm going to the bottom of the screen. No, that's not working. When is doing this? When ice is in water, it floats because it's less dense. So one way to think about that is, I'm gonna jump back. Switch it up rather than thinking about water and ice. What is more dense? And don't think about the word density, but instead think about liquid water. I'm going to put this as an A, or B, a penny. And rather than thinking about the specific question that's being asked, instead visualize that. What happens to a penny when you drop it into water? What does it do? I'm looking for one word. Sinks. Absolutely. So when something sinks, well, the more dense substance, sinks, and the less dense substance floats. So here what we have is a series of different liquids. I'm going to give you letters A, B, C, D, E, and F. Based on those letters, motor oil is A, vegetable oil B, hand soap C, milk D, corn syrup E, and honey F. Which one of these substances is the most dense? F, honey. Which is the least dense? Perfect. Now, when you look at all of these, if you were to imagine where water would fall, well, water is going to be a little bit less dense than milk. So water might be right about here or here. It depends a little bit, or sorry, water would be above this, so it'd probably be here or here, is my guess. So things separate based on their density and a comparison of their density. Now, in order to calculate density, you have to have a couple of things. You have to have a designated volume and a mass. So here what we have is a liquid. That liquid has been poured into this graduated cylinder. This piece of instrumentation, or this instrument here, is known as a graduated cylinder. And we have approximately, I'll call that about 83 milliliters. Or sorry, 8.3 milliliters. Now, this tool right here gives you the opportunity to determine the density of a liquid. And all that you're going to do is you're going to use this container, or go through this exercise. Let me grab the link. Sorry. So this is going to be a part of the activity that you're going to do this week, which will be posted later today, um, you're going to fill this graduated cylinder with water. You're going to know the volume of it. And then you're going to add a solid to it. Or sorry, that would be where you would add a solid to it. Now, we can also determine the density of a solid. So if we look at these two samples, they're both pure copper. So they're both pure substances. Which one is more dense? A, B, or C? C is neither. A, we've got the object on the left. That's the more dense one. B is the other object. Or C, neither of them's more dense. Spoiler alert, they are identical in terms of they are both solid copper. Go ahead and add to the chat which one is more dense. You got lots of C's there, and you're absolutely right. These are both pure copper, so they're both equally dense. So neither one of them is more dense than the other. It's very tempting to say, oh, well, it's B, because I can kind of visualize that object has been compressed. And then you look at A and you're like, well, I could imagine that would float because it's got so much surface area. It's been flattened out. You got a steamroller that just flattened it out. You put it on the surface of water, it's just going to rest on top of there. It's tempting, but that's incorrect. So the correct answer here is C. Neither one of them is more dense because they are the same material. Now, whenever we're determining the density of a solid, we use something known as displacement. So what we would do is, and this is another part of the activity that you guys are going to be doing. So we'll take this iron ball right here. You put that on a digital balance, and that's going to tell you this is 13.6425 grams. Okay, great. Then you've got a graduated cylinder, and that's set to 200 milliliters of water. You add this iron ball to this, and let's say that the volume goes up to 245.6 milliliters. Can you tell me in the chat what is the volume of this iron ball right here? 45.6. That's measuring volume by displacement. Because the water before the iron ball was at 200, then after we add the iron ball, it goes up to 245.6. The only thing that differs is the presence of this iron ball. And so our iron ball has a volume of 45.6 milliliters. Now, what does this mean for our density? Well, we calculate our density by saying 13.6425, our mass, over our volume. And we'd see whatever that actually is. Okay, can you give me a number in the chat if that makes sense? Can you give me a letter? Can you give me a number in the chat if you understand how to calculate the volume of this solid object? Okay. Now, this is a part of the activity that you guys, or the homework that you're going to have, where you have this set of different objects in this online tool that I'm going to share with you guys. And then you're going to have to identify what this solid is based on these different densities. And the reason for that is, if we look back right here, I told you that both of these are pure copper. They have the same density. So if I were to come up to you and I were to say, hey, I have this unknown sample, and I determined that the density was 19 point, let's just say 29 grams. Let's say it was really precise. And I've got 150 grams of it. Actually, let's just go with 450 grams. That's about 1 pound. If I had that much of this substance and I was like, hey, should I A, make soda cans from it, or B, sell it? Sell it slash hold it for monetary purposes. What should I do? I've got Julia's voted B. Didier B's, well, and I just came in with this random sample. Yeah, I would vote that I should sell it or hold it for monetary purposes. If I were to make soda cans from it, well, that'd be an expensive soda can. And two, one thing that we know about about gold is that it's very bendable, in which case it might make a weaker soda can than I really want. It might be that whenever I go to try to open it, it doesn't, and instead the tap just sort of bends. Okay, that's because we can use the density of a metal to identify it. And so what we can do is we can say, oh, well, based on the density of that, it is this object or it is this material. Now, that's something that we're going to do as a part of this activity. Same thing with this activity right here. I'm going to show you guys this one online real quick. Okay, just walk you through this one. Oh, good. So this tool right here is pretty cool. It's called PhET. It's hosted at the University of Colorado. It's lots of demonstrations of and visualizations of different concepts. So here what we have is different objects. We have a set volume. So I'm going to take this object that's 5 kilograms. Notice all of these are 5 kilograms. Does it look like answer A if they all probably have the same densities, or B if they have different densities? And your assessment is based on, well, I can see these objects. A is that they have different densities, B is that they're all the same. And we're inspecting them. They look a little bit different because I think everyone would agree that object A is larger than object B. B is larger than C and larger than D. Would anyone care to guess which one is the most dense using the letters on those different boxes? A, B, C, or D. Which one is the most dense? You got to vote for D? Yeah, okay. So let's go ahead and see. And, we can measure their relative densities by dragging and dropping them into the water. Okay, cool. That one floats. We've got 5 kilograms, 105 liters. So new volume for this would be, well, or the densities for object A is going to be approximately 1 kilogram per liter or 1 gram per liter. Or B is 1 kilogram per liter. Oh, A is 5 kilograms and it has a smaller volume, so it sinks. C sinks. D sinks. So let's see. Tell me, watch these numbers. What is the volume for object D? Okay, so our starting volume is 112.5 liters. and we go up to 113.75. So what's my volume for object D? Absolutely. 1.25. So all of these objects, they vary a little bit in terms of their density, and that makes sense because their volumes differ. The the drawing of these different objects, well, they're very similar to what the visual is. So now we can do this. We have unknown objects. So we could say, based on what these are, here's a series of different like known materials and their corresponding densities. Object 1B has a mass of 0.4 kilograms. Okay, so 0.4 kilograms. Let's see what our, so 0.4 kilograms. What is our volume for B? Oh, get out of there, A. Volume is 0.4 liters. Okay, so what is object 1B? What is its identity based on this density table? Well, let's think about that. 0.4 kilograms divided by exactly 0.4. It's water. Okay, great. Now let's go with 1C. Now it's tempting to look at 1C and be like, oh, that's gold because it's kind of yellowish. We got a mass of 19.32 kilograms. Now let's see its density, its volume. Surprise, boom. Volume, 1 liter. So what is object 1C? Gold. Wonderful. Okay. Can you give me a number in the chat if, oh, that makes sense, or a letter in the chat if you are mixed up on that? Okay. Okay. So this is the sort of thing that obviously you're not going to have the simulation on your exam, but if I were to give you information like this object has a volume of this and a mass of this based on this density table, what is that object? Give me a number if you think, oh yeah, I could totally do that, or a letter if you're like, uh, uh, I'll be there. Okay, cool. Um, so then that was, yeah, that's pretty much the end of that. Now what we're going to do is we're going to go on to, so that's going to be a part of your activity, your homework that will be posted on Canvas later today. Um, it's 10:45, so we're making good time. How do you feel about density? Give me a number if you're like, okay, I'm getting there, or a letter if you're like, I'm getting there. Okay. Okay. Well, I think that maybe whenever you see the homework problems, that will be a good indicator, or that will be like a good assessment of like the sorts of questions that I'm going to ask of you. And similarly, you do have a quiz today that opens at 11 a.m. and closes at 11:59 p.m. tonight. So that will also be a good kind of display of, hey, here's the sorts of questions you should anticipate. Okay, so now what we're going to do is we are going to begin talking about the periodic table. Pretty central to chemistry, pretty central to science in general. What is the periodic table? Which of these represents an element? Add to the chat. Is it A, B, or C? When we're looking for an element, we're looking for just one single thing. And so A, whenever I say it has one single thing, well, this thing right here, oh, dang it, that went a lot farther than I expected. What on earth? How did that happen? Okay, sorry about that, everyone. Um, okay. So B is correct because if you look at A, that's basically a water molecule because we've got the white ball, red ball, and then another white ball. Whereas in B, you've got two of them, but they are identical. C, well, you got this, which is different from these, and this, which is different from this. So that's going to be a more complex mixture. Now, when it comes to the periodic table, one of the things that's important to understand are a couple of different scientific laws. So, what do you notice about the mass in these? Well, and actually, let's go ahead and look at our before reaction. We have this right here is known as an Erlenmeyer flask. I'm just going to call it a flask. This is a graduated cylinder. Both of them have liquids in. So the mass of the glassware of the two different pieces of glass and the solutions equals 173.64. When we take the contents from the graduated cylinder and add them to the Erlenmeyer flask, well, that's going to also equal 173.64. I think that everyone would pretty safely agree that, yeah, the solution in our flask from before and after the reaction, it's different. It's clear before the reaction, and then it's cloudy and dark after the reaction. It's even kind of a different color. It's a bronzish color. Well, that's because we took from the grad cylinder and added it to there. But this solution and this solution, they're different in terms of how dark they are. One of them is kind of difficult to see through, and then one of them you can't see through it at all. After the reaction, you can't see through that solution. It's a very dark, cloudy solution. Now, that is known as the law of conservation of mass. So matter is neither created nor destroyed during a chemical reaction. Um, Another illustration of that is this right here. Mercuric oxide. This is a compound made up of mercury, Hg, and O, oxygen. Well, when you burn this, when you put this in a test tube and you expose it to heat, what's going to happen is that the oxygen that's in here is going to burn off and it's going to be released as oxygen gas, O2 gas. What's going to be left behind is the metal, that mercury. So we're going to have from 100 grams of mercuric oxide, we're going to have 92.61 grams of mercury and 7.39 grams of oxygen. Now, if you do 200 grams of your starting material, you're going to get 2 times as much mercury, 2 times as much of your oxygen. And similarly, you've seen a baking soda volcano where you mix vinegar and baking soda, and lo and behold, a gas is released. Well, that gas, CO2, is released. If you took the mass of the baking soda and the mass of the vinegar, Well, that is going to be equal to the mass of the CO2 and the liquid, which in this case, in this specific reaction, the liquid that you make is water, but it's going to be the mass of the water that remains. Now, another important rule, and we're kind of breezing through these because of the fact that they're going to be more important later on when we talk about chemical reactions. Um, but we convert things, we rearrange atoms to make new products. CO plus O2 yields CO2. Carbon and oxygen can rearrange in different ratios, but CO2 is the gas that you exhale. That is a defined proportion. Whenever you talk about carbon dioxide, that is always going to be one carbon and two oxygens. It's never going to be one carbon and one oxygen. Our law of multiple proportions, well, that is where we can rearrange these atoms in different forms. We can have one carbon, one oxygen, one carbon, two oxygens. They're both legit compounds. They are different from one another. And they are both separately defined as CO and CO2. Now, we'll revisit these later on, but all of these are kind of summed up in what's known as Dalton's atomic theory. And there's a bunch of theories to explain different aspects of chemical reactions, which and important things about kind of the rules of like the way that chemical compounds rearrange. We'll revisit these tomorrow, but for now, let's go into the periodic table and what you see when you look at the periodic table. Give me in the chat a number if you have ever seen the periodic table, or a letter if you say, no, but I got a kitchen table. Okay, great. Now, when you look at the periodic table, there's a lot of stuff on there. This is one good example of what's on there. A nice little square, and the general shape of the periodic table looks a little bit like this. Choop, choop, boop, 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 boop. And then this little cutout section right here. Boop, boop. Okay. Give me a number if you think, man, that's a better rendering of the periodic table than that rectangle or that square that he drew earlier. And a letter if you think my drawing skills, they have room for improvement. Okay, good. Thank you. I'm very sensitive. I could not take that sort of criticism. Um, but I appreciate the feedback there. Okay, so that's roughly what the periodic table looks like. A little bit of a spoiler for you. We're not going to talk about this stuff. These are the lanthanides and actinides. They're not super relevant. My background is in biochemistry. They're almost irrelevant to biochemists. Whenever I talk about the periodic table and relevancy to a biochemist, I would say that where I'm scribbling is where stuff is not relevant to a biochemist. So it's kind of funny, like, oh yeah, we've got this periodic table with 100 some odd elements, but you're a biochemist, so you really only care about 7 of them, and that's pretty accurate. Can anyone name an element aside from Fe that is not okay? Aside from carbon, oxygen, hydrogen, or Fe, name an element. Add the symbol to the chat. Ag, silver, Au, gold, nitrogen, potassium, lead, boron. Okay, great. CH. There's C, there's CR. What is CH? PO. Well, okay. Ashton, thank you very much. We got PO. Capital P, capital O is going to be phosphate or phosphorus and oxygen. PO, chlorine. Okay, so chlorine is Cl. Okay, but you bring up a very good point. whenever we look at the atomic symbol or the chemical symbol, it is either, it's one of like three different things. Capital letter followed by a lowercase letter, capital letter alone, or in rare instances, it's a capital letter followed by two lowercase letters. So that's pretty much the standard for your atomic symbol. Now, every single element on the periodic table and every single one of those cells that you see on the periodic table also has at least two other numbers. Those numbers are to talk about the mass of one of those single atoms, or they are what's known as the atomic number, or Z. Has anyone ever heard of a subatomic particle? If you've ever heard of subatomic particle, add a number to, or a letter to the chat. A letter, a letter, a letter. Okay. Now, here's a bonus point. I'm going to add this final exam bonus point. Just because I think that it's most valuable to add bonus points to the final exam as opposed to anything else. Here's the thing. I'm going to ask a question. And I want you guys to answer with your own head here and nothing else, no other resources. If within the first 4 responses, I get a correct response, there will be 1 bonus point added to your final exam grade. So within the first 4 responses, and this is tough because you're all in different places. Tell me one of the 3 subatomic particles. Oh, Devin, tell me the identity of. Okay, good. You know what, Devin, you got me there. So that's 1 bonus point because I hadn't thought of that. And then within my first, well, Devin got me with the first response. And then Sparrow, you got me with the right response there. So that is like, I gave you answer options A, B, and C, and you guys just went, yeah, but what about answer option D? Did you think about that? And I think I didn't. And so that's actually gonna pay you back. So that's gonna be 2 bonus points. So man. I'm not even mad. I'm not mad. Because, if you guys do well on your exams and you guys get strong grades on it, that's not going to make me upset. I'm happy about that. Man. I'm going to have to do some soul searching this afternoon because, man, you got me. Dang it. Dang it. Not mad. Like I said, I am not mad. I'm just like, dang, you got me. I feel like I just parallel parked when I didn't need to. Like, dang. Okay. So 2 bonus points on the final exam. Good job. Okay, so we've got 3 subatomic particles: protons, neutrons, and electrons. We're going to talk about all of those. But most importantly, this atomic number right here, that tells you the number of protons. So if I told you that I had 1 atom of iron, well, that single atom of iron has 26 protons. Now, Well, heck, I had this as part of my plan anyway, but I'm going to put back out there. For one bonus point, what is the charge of a proton? I'll give you a little bit of a hint. Never mind, I'm not even going to give you a hint because you just got the answer. Exactly. A proton has a positive charge. Our subatomic particles have different charges. Protons are positive. I'm making my note. Oh. Protons are positive, neutrons are neutral, and electrons are negative. So if you have an equal number, and this is an important part of chemistry, if you have an atom that has 26 protons and 26 electrons, what is the charge of that atom? 0. Those charges cancel one another out. Something that's positive and negative, or if it has something that's positive and it has something that's negative, they cancel one another out. Okay, now we'll move on from that. Here's our periodic table. If you look at this, almost all of, let's see, did I find? No, now I'm not seeing the three-letter characters, so I'm going to go back. I could have sworn there was something with three letters, one of those lanthanides and actinides. Okay, so every symbol on the periodic table, I revised this, is an uppercase and a lowercase character. See, these guys right here, these are relatively new. And I'm not joking about that. They were like these right here, these last like 5 or 6, they're not naturally occurring. These are things that let's see, nuclear chemists basically try to make, in the sense that they take something like this right here. I believe so. I'm confessing this is like outside of my area of study, as is the case with these guys. Let me go back and revise my summary of here's what a biochemist knows, or what a biochemist needs to know about. Wait, no, I did use cesium. Oh, okay. Okay, so as a biochemist, these are the elements, the ones that don't have any scribbling on them. Those are the ones that I encountered at any point in my research career. So not a whole lot of them. But these down here, these nuclear chemists, those are ones that are fairly recently discovered. And one of the fun things about them is this right here, TS, or tennessine. Does anyone want to guess where it was discovered? Yep, Tennessee. At Vanderbilt University, they discovered it. Or they not discovered it, but they like stabilized it. Um, and so as a result, they were like, well, we're going to call it tennessine because we are here in Nashville, Tennessee. Um, then livermorium was discovered in, I think, now I'm thinking Livermore, but now I think it was at a Lawrence Livermore Research Institute, but it might have been in Liverpool, England. I don't know. Same. But I'd have to look that up a little bit. And so then lots of the other ones, Einsteinium, Mendelevium, these are named after people. Um, Lawrencium. Yeah, so that's what I would think Livermorium would maybe be in Liverpool. But I could look that up. Moscovium. And that was, you're right, discovered in Tampa. Not really. Not really. I was just going with Moscow's a city in Russia, St. Petersburg's a city in Russia and in Florida. So that's how I arrived at Tampa as the right answer. But like I said the other day, I have ADHD, and that's how my brain works. Okay, so this is the layout of the periodic table. If you take any one of these symbols, this periodic table doesn't have a lot of information on it. It's got the full name of the metal or of the material. It's got, if we take this right here, this large one, we've got our atomic number. It's a whole number. It's got the atomic symbol. It's got the name and then the classification of that element. So if you notice everything going down, or almost everything going down, has the similar classification. It's kind of tough to see. Let's go with here. Vanadium, niobium, tantalum, and dubnium. These are all, it's tough to see that, but I promise you they say transition metal, transition metal, transition metal. These are all transition metals. And that has to do with basically their chemical properties. How reactive are they with this, or how reactive are they with that? Now, these alkali metals, starting on the far left of the periodic table, all of these right here, specifically with lithium, sodium, potassium, rubidium, these are highly reactive. And to illustrate that point, dang it, that video doesn't play in the, this is where I think, man, internet, why are you so dumb? But not internet, computer, why are you so dumb? So this right here is a, I haven't looked at their cookie policy. I want to make sure that I'm okay. We won't blow it up to full screen. Okay, so here what we have is 3 glasses of water, or 3 containers with water. This is H2O. Not necessarily tap water, but this would be like you went to the grocery store and you got some distilled or deionized water. So something that all the minerals have been taken out of. And what happens whenever we put different metals in there? Boom. We'll jump ahead a little bit. Okay. And now we're going to go back. We're going back just because this is one of those rare instances where I think that describing the events are actually more inviting and enticing than watching the events unfold. So that video was somebody with pure lithium, sodium, and potassium. Sodium, yep, there we go. Give me a number in the chat if you've ever heard of or seen sodium in like a formula, or maybe whenever I wrote it down the other day. Yeah, sodium. Okay. So Na versus NaCl. Okay. NaCl is a compound. It's what's known as an ionic compound. And we're going to get more into those details in just a little while, but Na right here is actually Na plus, and Cl is Cl minus. Okay, now with that in mind, give me a number if you think that Na and Na plus are the same, or give me a letter if you think, wait a minute, one of them has a plus and one of them doesn't. I think they're different. Give me a letter if you think they're different, or a number if you think, yeah, they're absolutely the same despite that. You're right. They are different. What makes them different from one another is a subatomic particle. So I'll just add in here a subatomic particle. Sparrow, and I apologize if I'm not pronouncing your name properly, but you're absolutely right. They have one of them has a charge and one of them doesn't. So subatomic particle makes these different. Specifically, well, let's jump back for a second. Our atomic number. Can you Okay, thank you very much. Can you tell me my atomic number represents which subatomic particle? Is it the protons, P for protons, N for neutrons, or E for electrons? Protons. Our subatomic particle represents our protons. Okay. Now, if I tell you, hey, I found an atom, one atom happens, don't worry about it. One atom, and you know what? It has 32 protons. I shrunk myself down to the atomic level and looked at it, and I found it at 32 protons. Give me the symbol of that one atom, looking at the periodic table here. Perfect. Germanium. Okay, germanium has 32 protons. Now, if I said, oh, I found one atom of Ge, and it has 33 protons. Give me a number if you think, oh, neat, or a letter if you think, no, that's not right. That's impossible. You're right. It is impossible. Because if I found one atom, let's just scribble that out for a second. If I said I found one atom of something that has 33 protons, what is that something? That's right, arsenic. So whenever you talk about a like an atom with X many protons, the number of protons is never going to change if you're talking about the same element. So what I mean by that is every single atom of, let's go with Li, has how many protons? Add that to the chat. 3. Perfect. So then if we jump over here, we've got 3 different subatomic particles: protons, neutrons, and electrons. Neutrons, we remember, those have no charge whatsoever. Protons have a positive charge. Electrons have a negative charge. If I tell you that Na has, let's see, let's go back. Na has 11 protons. This Na right here, how many electrons does that have to have? 11. Okay, that's why it has no charge whatsoever. Could you give me a letter if you follow that and understand this idea right here? And give me a number if you're like, wait a minute, stop the press. Okay, so another way of looking at this, and I'm going to come over here and draw this. One of my favorite songs of all time is Lithium by Nirvana. And I like that song because it's a really great song, but I also like it because it's helpful for me whenever I think about atoms. A lithium atom has 3 protons. So I'm going to draw a lithium atom. 1, 2, 3. Has 3 protons. A lithium atom with no charge with no charge whatsoever has 3 protons and 1, 2, 3 electrons. So add to the chat, what is the charge of that lithium atom that I've got in that big circle there? Nice. Okay, I'm going to update it. What is the charge of the lithium atom that I have in that circle there? Plus. Okay, now what is the charge of what I have in there right now? Perfect. Perfect. Okay, so now thinking about that, this right here, I'm going to write my symbol Li minus. Okay, and then I'm going to change it. I'm going to get rid of that. I'm going to get rid of an electron. Li is what's shown in that circle. And then I'm going to get rid of one electron, and that's Li plus. Did I ever change the number of protons? Yes or no? Y or N? No, I never changed the protons, because if I change the protons, then I'm changing my element. Now, let's go back up top here to sodium. How many protons does this sodium right here have? Perfect. It's 11 protons. Okay. Now, how many electrons does this Na plus have? Less than 11. How many less? And that plus one less. Perfect. So would you agree with me that 1 less than 11 is 10? Perfect. Okay. So the difference between Na and Na plus is a single subatomic particle. Can you give me a Y if you follow that, and an N if, wait a minute, huh? Okay, so that's all that makes these things different. So what this video was showing was we got some of this stuff right here, some of this Na, and dropped it in here. And slowly but surely, well, that Na has a chemical property in that it will react with water. And whenever Na reacts with water, it converts to Na plus. It loses one electron. When it loses that one electron, it kind of begins to look like this. It loses that electron and gives off a lot of energy. It violently loses an electron. And arguably, it starts a fire, or a little bit of a fire. So this is the loss of one electron. So Na losing one electron kind of violently happens. Now, this model that we saw in this video, it's a very small amount of sodium and a very small amount of a liquid. Think if you raise that up. Think if you got like 10 pounds of sodium and you had like a swimming pool. Do you think that you would be able to hear that at a Y or an N? Do you think that a pure metal like potassium or sodium or lithium is a part of a firework or fireworks? Yeah, because whenever they go up into the upper atmosphere and they get exposed to the amount of humidity, the water that's in the atmosphere, they're going to pop, and they're going to violently do so. Okay, so alkali metals are an example. When they lose an electron, they're going to violently do it. They're going to release energy. Now, this is something that we will revisit later on, but I want you to have this foundation of every element has a set number of protons, neutrons, and electrons. And if they gain or lose electrons, which electrons are the only thing that can be gained or lost, if they gain or lose them, that might happen in a very dramatic and violent way. And not violent like it's going to punch somebody, but instead like it could cause an explosion. Okay. Now, atoms and molecules. And I think that this is going to be our last slide for today for the slide deck, because that's going to make. Okay, actually, you know what? I've got 3 slides after this, and then 3 more slides. If we finish this, then I will jump on tomorrow at 10 a.m. for office hours for anyone who wants to review or ask questions. But we will have finished up what I wanted to finish for the week. If you want me to go ahead and finish these out, then add to the chat a Y. And then if you don't want me to, add to the chat a N. We'll stop right here. Now, with that in mind, just so you guys know, I'm getting lots of positive feedback there. If you join tomorrow and you're like, hey, could you go over everything from yesterday, Wednesday? Yeah, that's what I'll do. It can be like a one-on-one learning session or a one-on-one tutoring session. I have no qualms with that. But if you are like, I've got it, it's recorded, I can watch it again if I want to, then you do not need to come to the Zoom meeting tomorrow. Is everyone clear on that? Give me a Y if you're clear and N if I'm mixed up on that. Okay. Okay, cool. So we're going to finish this out. Atoms versus molecules. This is an important distinction. A molecule is a group of atoms chemically bonded to one another. Oh, yeah, I just went. Yep. There we go. These are bound together. So here we've got a water molecule. We've got oxygen, hydrogen. Those bond together. So connecting. So a visual of this is that in a water molecule, this image right here is kind of by design. The oxygens here and here, they are not in contact with one another. They are only in contact with the oxygen. Sorry, the hydrogens are not bound to one another. Hydrogens not touch each other. They only touch the oxygen. Now over here, we've got carbon in the middle. And then O, it's magic. Ow, chat box. Ugh. Get out of here. Go. No, that's not right. That's good. Nope, that's not right. But there we go. So this is COO, also known as CO2. When we got something like this, well, sheesh. There's a lot to decipher here. The first thing that's worth deciphering is the identity of the different atoms. So let's go through there. H, C, N, C, N, O, C, H, N, not M, Joel. C, N, C, H, oxygen, H. Now, let me ask you this. In this molecule, how many nitrogen, or actually, let's go ahead and put together the formula for this structure. What I always like to do is I like to think, okay, what do I have? I've got carbon, hydrogen, nitrogen, and oxygen. I'm going to count off the oxygens first. 1, 2. Nitrogens. We'll go on there. 1, 2, 3, 4. Yep, I got all my nitrogens. Hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Did anyone get a different formula? Or let me rephrase that. Did everyone follow how to put together this formula? Add a Y or an N to the chat. Okay. Follow-up question. Did anyone get a different formula? Y or an N? If you did, let me know. Okay, thank you. Yeah, I'm kind of cross-checking it again. I think that's what we got. C8HN or H10 N4O2. Now, my question for you guys. Oh, Heather, that's a fantastic question. Typically, or when you get a complex molecule like this, there are some rules that you do follow. Typically, carbons and hydrogens are going to be next to each other. And then what you're going to do is you're going to go farthest to the left. You're going to use the periodic table, and you're going to look at this and say, okay, which elements are farthest to the left? Okay. And what I mean by that, and to kind of follow up on this, is there are rules so for your question, there are rules. So it cannot be in any order. There are rules to follow. We will get those rules later on. Typically, as if you're like, okay, what's a big rule that I can follow? Put C and H first. Put those next to each other. And then what you're going to do is basically after that, farthest to left on P table. And you might be thinking, oh, so you got to have the periodic table memorized? I would say no, because what I would say is, if you remember what I showed you guys with respect to like, hey, I'm a biochemist, and here's the elements that I am familiar with and that I needed to know the most. You really don't need to know the entire periodic table. You need to know kind of the order of in the organization of like 8 to 10 elements, and you're good. And so we would take this and say, okay, CH first, and then we'd say, okay, nitrogen or oxygen first. Well, nitrogen is farthest to the left, so I'm going to put nitrogens, put all those, and then my oxygens. Does that answer your question, Heather? Okay, cool. Yeah, you asked a yes or no question, and I gave you a 2.5 minute response. That didn't, yeah, sorry about that. Okay, now my question for you guys, answer with a Y or an N. Looking at this molecule, are there any carbon to oxygen bonds? Y or N, if there are carbon to oxygen bonds. Remember, the carbons are the black balls, and then the oxygens are the red ones. Okay. Yes, there are some. Yep, you're absolutely right, Heather. Here and here. So there are 2 carbon to oxygen bonds. Okay. Next up, and this is the sort of question that I want you guys to be able to answer. Are there any nitrogen to oxygen bonds? Y or N? No, there aren't, because the oxygens are only bound to carbon. So the point here is to be able to decipher like what is connecting these two things and what are like being able to identify them. Now, with that in mind, this right here, this bond is electrons. These electrons right here, represented by this bond, are being shared by this nitrogen and this carbon. Now, write the expression from this structures, or from the structures, H2O, H2O. H2O. Let's say, which is more correct, A or B? Is it more correct to say we got three H2Os or H6O3? Answer in the chat. Which is more correct, A or B? A is the correct answer. And it's tempting to say, oh, well, B, that sums up everything. But is this molecule bound to this molecule? Which is that bound to this? No. These are all independent molecules. And so we write them as independent molecules. So that's why we would say, well, there's three H2Os. Now, our last slide for this week, how many hydrogens are in ibuprofen? Ibuprofen has a formula of C13H18O2. Perfect. C. Now, add to the chat, how many hydrogens are in 3C13H18O2? 54. Because what we got to do is say, okay, well, in one of them, there's 18. 18. 18. 8 plus 8 plus 8 is 4. 1 plus 1 plus 1 is 3, plus 2, 54. So if you had 3 molecules of ibuprofen, that means you total have 39 carbons, 54 hydrogens, 6 oxygens. Okay, is everyone good? Because that's where I'm going to stop. And like I said, tomorrow I will be on at 9 a.m. for office hours. And I'll be there from 9 until 10. Then, do ionic charges... Ooh, great question, Sparrow. Do ionic charges only change when an element bonds or reacts? That is a fantastic question. And to answer it, yes. The ionic charge, or the charges on an ion, is only going to be kind of relevant, or it's only going to change whenever something reacts with something else. So it's only going to lose electrons if it's released in the atmosphere. Then it will lose or gain electrons because there's oxygen and there's nitrogen questions. Yeah, and it just has like this kind of this desire. Yeah, it's got to change. It's got to share them. And then there are other things that have to gain them, that have to collect them. So I'll be on from 9 to 10, and then I'll switch over to our classroom Zoom, and I'll be here. If you want to come by and ask questions, you're more than welcome to. I have no problem one way or another. If you don't, if you're like, well, I'm going to start my weekend early, start your weekend early, and enjoy it. But then we'll keep with our Monday schedule. So the stuff that's online for Monday's lecture, we'll jump into that on Monday. So I'm not going to, as much as I think that it's good to like be efficient and get through stuff, I don't want to be like, hey, yeah, the class was scheduled for 5 weeks, but we did it in 7 days. I don't really think that's a good idea. Yeah, group chat. I think GroupMe's, I know that in my online classes, people like to set up GroupMe's. One way that people do it typically is through the discussion board on our Canvas site, which I believe you guys have access to. I'm going to go ahead and